All right, last class we had a riveting time, an absolutely wonderful time, roaring, racing, ripping through lots of content. And we got to complete ionic and net ionic equations, which was the whole goal of the roaring, ripping, and racing. Other things that fall into the category of aqueous solutions and reactions are acid-base reactions, which we'll be doing next week in lab. An acid-base reaction is also called a neutralization reaction, or put together an acid-base neutralization reaction. In these, an acid reacts with a base, and the two neutralize each other. So we lose the action of the acid, we lose the action of the base because they act on each other. And these produce water, and sometimes there's also a weak electrolyte that gets produced. There's also gas evolution reactions, the evolution part referring to them being produced. So a gas producing reaction. It produces a gas, it's often seen as bubbling. Some of these are also acid-base reactions. There's a couple that you'll get to memorize. Before we can talk about acid-base reactions, we need to talk a little bit about acids and bases and what are those. And so we'll be talking about our Arrhenius definition. Thank you, Svante Arrhenius. So our Arrhenius definition of an acid is a substance that produces H+ in aqueous solution. So it makes H+ when you put it in water. That's our Arrhenius definition. What this actually means, this H+ doesn't exist for very long. Protons by themselves don't just float around in the world or in solution, certainly, for very long without getting gobbled up by other things, and the thing that gobbles it up is a water molecule. So this H+ can react with an H2O. The oxygen has some extra lone pairs that it can use to latch onto this H+, and it forms a hydronium ion, which is one of the ions that you get the privilege to memorize. For all intents and purposes, H+ is the same as H3O+. So if you see H+, you should read, if we're in aqueous solution, at least H3O+. If there's water around, it will be as H3O+. It won't be just H+ floating around. But just to save a small amount of time, we'll often just write H+. A lot of acids, things like HCl, are what we would call monoprotic. They produce one proton. There are also things that can produce more than one ionizable proton or have more than one proton that can be released. And we call these polyprotic acids. So they may have 2 or 3 H+ that they can release. And the way that we know this isn't always true, but oftentimes we can tell that it's a polyprotic acid because it's got multiple H's in front. This is not always the case, but often it is. So the number of H in front equals number of ionizable hydrogens. Again, this isn't always true, but it's often true. Since those H's in front are what make something an acid. You will not always see all of the H's written in front. Sometimes, depending on how people like to write it out, they might just put all of the hydrogens in the middle, and you would just have to know that it's an acid based on context or somebody naming it as an acid. Usually in this class, you'll see the hydrogens in front to let you know that it's an acid and that it's mono, di, or triprotic. Our Arrhenius definition for a base is a substance that produces hydroxide, OH-, in aqueous solution. So Arrhenius base makes hydroxide when you add it to water or when it is in water. For example, sodium hydroxide. Sodium is always soluble in water, And so you add sodium hydroxide to water, the sodium and the hydroxide get separated. And so sodium hydroxide is an arrhenius base. There are also bases like NH3 that don't contain OH minus ions, but instead produce hydroxide by pulling a hydrogen off of water molecules. These are not arrhenius bases. NH3 is not an arrhenius base. It is a base, it's just not an arrhenius base, because it doesn't directly produce the hydroxide. It doesn't have hydroxide that it can release when it goes into water. Some bases also produce 2 moles of hydroxide per mole of base. For example, things like strontium hydroxide. We've got a little subscript of 2 on our hydroxide, so each of these molecules, each of these formula units can produce 2 hydroxides. You might see that sometimes called dibasic. Okay, so these acids and bases can react to form water. The H plus from the acid and the hydroxide from the base react to make water. So in an acid-base neutralization, our acid and our base neutralize each other by producing water. The water is the H plus the OH minus. It's sometimes helpful to write it out that way as H plus OH minus when you are balancing these. So if you're balancing a chemical reaction that's an acid-base neutralization reaction, it can be helpful to separate these 2 things out. They're really combined, but it can be helpful to keep track of them separately so that you can just count your hydroxides and your H pluses. The other thing that's formed is typically a salt. In this case, it is salt, sodium chloride. A salt is an ionic compound. That'll usually be soluble. Again, in this case, it just happens to be that the salt is salt, table salt. It's not always going to be sodium chloride. So our net ionic equation for an acid-base reaction involving a strong acid. Who remembers what a strong acid, what the strong part means? We could also use it in the context of electrolytes. Strong electrolyte. Anyone remember? So strong acids completely separate, strong electrolytes also completely separate. And they would have a one-way arrow indicating that the reaction only proceeds in the forward direction. It does not proceed in the reverse direction. Lots of acid and base reactions are not particularly exciting. For example, this is HCl, hydrochloric acid, plus NaOH, sodium hydroxide. They're both clear solutions. You mix them together and they produce water, which is also a clear solution, and sodium chloride, which if you've made like a salt wash gargle or something like that, you would know that that's also a clear solution. So we're mixing clear solutions to produce clear solutions. It's not particularly exciting, but that's what's going on. Here are some of our common acids and bases. This is not an exhaustive list, just some of our acids and bases. Some of these are strong, the ones that are listed here. A note about sulfuric acid, the first one is strong, the second one's weak. This was also mentioned on a slide previously. I don't remember if we go into depth on why that is. If we do, it'll be later in the class. And since strong means that they completely dissociate or completely separate, completely ionize, weak means that they do not completely ionize. So things like formic acid, acetic acid, hydrofluoric acid are not going to completely separate into H plus and F minus, for example. there will be some units of HF that are floating around in solution. We can write out equations for acid-base reactions. So we want a molecular and net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. Fortunately, we don't have to tap into our nomenclature knowledge to solve this problem. HBr is a binary acid, hydrobromic acid. LiOH is an ionic compound. Lithium always has the same charge, so it's just lithium hydroxide. These are both aqueous as described in the question. What is one of our products going to be when we have a reaction between an acid and a base? Water. So this goes to produce H2O as a liquid. And what's the other thing? Salt. A salt. In this case, the salt that's formed from lithium ion and bromide ion. Since they're both one charge, one's one positive, one's one negative, we just combine them together. It's just LiBr. And since we have lithium in there, and lithium's an alkali metal and it's always soluble in water, we are going to write that in as aqueous. So this would be our molecular equation. Is it balanced? Yes, it is balanced. We've got the H, we've got the OH, together those make H2O. We've got the lithium, we've got the bromine, or the bromide, together those make lithium bromide. So it's balanced, it's a 1-to-1. If we wanted to make the net ionic equation, what do we do? We could write the complete ionic equation, and then from the complete ionic equation, what would we take out? Soluble substances is correct. I was looking for spectator ions, but they are soluble substances. So we'll go ahead and do the complete ionic equation just for fun. Okay, so that's everything that we've got on the left side. They're all aqueous, and so we separate them out into their ions. I'm omitting the AQs just because I don't want to write them all. And then we've got H2O, which is a liquid, and so we keep that together. And then the other things that we have are the lithium ion and the bromide, and since those are aqueous, we separate them out as well. So that would be our complete ionic equation. We also want our net ionic equation. So we're looking at writing just the things that reacted, just the things that actually changed. The things that didn't change were the bromide and the lithium. One way that we can see that is we've got lithium bromide that's aqueous at the end. It didn't react. Those were aqueous before, they're still aqueous afterwards. So if we just remove those two things, then that'll give us our net ionic equation. So we could skip straight to the net ionic equation. Okay, so what's left after that? H plus OH minus goes to H2O. We can also do a similar thing for this reaction between aqueous HCHO2, which is a weak acid, and aqueous NaOH. We're reacting an acid and a base. What are the products going to be? We're going to have water, and we'll also have a salt. In this case, that's going to be Nacho. 2. Any guesses on which of those 2 is the product? The thing that's new that was formed from the aqueous solutions? It's our luchador. No, it's not our luchador. Our luchador is not new. Our salt is not new. Nacho, not new. The water is the new thing. And if we wanted to, we would. We don't want to, so I'm just skipping to the surprise. Wow, it's an acid-base reaction. The acid and the base react and they form water. Doesn't this look very similar to our net ionic equation from our other acid-base neutralization reaction? Someone say yes. Thank you. Yes. It's the same. It's the same net ionic equation. And this is not always true, but generally when you react an acid and a base together, the fun product that you get is the clear solution water. What we'll be doing next week in lab is an acid-base titration. So in a titration, a substance that we have in a solution of known concentration is reacted with another substance in a solution of unknown concentration. We know what the solutions are, we just don't know the concentration of one of them. So one of them will be the acid, the other one will be the base. And because we know what their reactants are, and we know the ratio that they react with each other, we can do some calculations to figure out the concentration of the unknown. And so the way that we do this is we add one solution to the other until the reactants are at their stoichiometric ratio, the equivalence point. At the equivalence point, the concentration of the H plus is equal to the concentration of the OH minus, the amount that we added. So the amount of acid that we added, we've added enough acid that all of our base is reacted, or we've added enough base that all of our acid is reacted. Basically until the acid and the base completely neutralize each other. And some of you, but maybe none of you, might be thinking, well, how do we know that we've reached the equivalence point? And that's a great question, because we're adding a clear liquid to another clear liquid to produce a clear liquid. What's the indication that we're at the equivalence point? And we'll talk about that in 2 bullet points. So knowing that we're at the equivalence point, that unlocks our ability to use our stoichiometric ratio from our balanced chemical equation, which we would have been given or come up with ourselves because we know the identity of the acid, we know the identity of the base. And so we can calculate the unknown concentration with some stoichiometry. Again, because the reactant and the product solutions are both colorless, we would use an indicator, and there's a lot of indicators. Indicators are just color changing chemicals. There's a whole slew of indicators. Typically, we just use phenolphthalein, which is not written on here, but I think we'll see on the next slide. And so for those of you that aren't freaks about spelling like me, you can thank your lucky stars that you don't have to know how to spell phenolphthalein. It's not going to be on a spelling test. You'll see why I'm saying that in a second. At the equivalence point of an acid-base titration, our number of moles of H plus equals the number of moles of OH minus. That's just restating this point about the equivalence point. Okay, so here's what an acid-base titration looks like. Typically, we're going to have the hydroxide, sodium hydroxide, potassium hydroxide, some other form of hydroxide, a base, in our burette. So we'll have our burette, use that to dispense and measure the amount of hydroxide that we add to a solution of a known acid. As we're adding that base in, our acid is getting used up. We can see that in this middle slide. It's also going to produce a little bit of color temporarily because of the phenolphthalein indicator that we've got in there. Isn't that a fun spelling? Isn't that so cool? So we're going to use phenolphthalein indicator. And when we reach the equivalence point, the pH of the solution is such that the phenolphthalein indicator changes color and it remains pink permanently. It also kind of looks like fuchsia. So something like this. This image, this color, I would probably say we've gone a little bit too far. We've saturated our indicator, but that's generally the color that we're looking for. A permanent pink color remaining in our solution to indicate that we are at the equivalence point. How do we do these calculations? Here's how we do those calculations. So we are doing a titration. The titration, just meaning we're mixing acid and base together, of a 20 milliliter sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of this concentration of potassium hydroxide to reach the equivalence point. We want to know what's the concentration of the H2SO4 sulfuric acid solution. One of the things that we will definitely need anytime we're doing a titration is we'll need a balanced chemical equation. There are some tricks that would let you not need a balanced chemical equation, but it's always safer for us to go ahead and just write out a balanced chemical equation. So our first reactant is our H2SO4. This would be soluble in water. Our other reactant is KOH. What is one of our products? Water, H2O. What's our other product? A salt. And our salt is going to be made of the things that don't go to become water, the K and the SO4. What's the charge on potassium when it's an ion? It's a 1 plus. So K plus. What's the charge on sulfate? 2 minus. So we've got SO4 2 minus and K plus. We are going to need 2 potassiums. So it's K2SO4. Okay, so K2SO4 is our other product. Is this balanced? No, it's not balanced. What's one reason that it's not balanced? Yeah, our potassiums are not balanced. We've got 1 on the left side, we've got 2 on the right side. So we're going to need to add a coefficient of 2 in front of our KOH to get our potassiums balanced out. When we did that, we changed the number of hydroxides that we have. We have 2 hydroxides on the left side. How many hydroxides do we have on the right side? 1. How do we have 1 hydroxide on the right side? We don't have hydroxide on the right side. H2O is secretly, or another way we can write it rather, H plus OH minus. This is why I say it can be helpful to write it out separately as it's H plus and OH minus together. So we've got 1 hydroxide that's in this H2O. So to get those to balance out, we add a coefficient of 2. Now we've got 2 hydroxides and 2 H pluses. Conveniently, we've also got 2 H pluses on the left side. We've got 1 sulfate on the left side, 1 sulfate on the right side. So now it's balanced. The other way that you can figure this out without having to write out the product side is we need an equal number of ionizable hydrogens, the H2 in front of our SO4. We've got 2 hydrogens on the left side that can react, and that needs to be equal to the amount of hydroxides that we have on the reactant side. So we would also have 2 there. So just looking at the acid part, the base part, we can figure out that we need a 2 in front of our KOH without even writing in the product side. Optional. Okay, we've got 2 chemicals in this problem. One of the chemicals we have 2 numbers for, the other chemical we have 1 number for. So we're going to start with the chemical that we've got 2 numbers for, the KOH. We've got 22.87 milliliters and 0.158 molar KOH. It doesn't really matter which one of these we start with, but there's one that I would prefer to start with, and it's the one that's the simpler unit. You may remember that molarity we can do a fun trick with, since molarity equals moles over liters, we can turn this molarity into moles over liters. So now it's actually a conversion factor. It's the amount of moles in 1 liter of the potassium hydroxide solution. Since that's a conversion factor, I want to start with the volume. And you may choose to start with this in liters. I'm going to just assume that we can do that without me having to write it out. So we turn it into liters. And to figure out how much of the sulfuric acid that we have in the solution, the moles of the sulfuric acid, so that we can calculate the concentration of the sulfuric acid, we need to know also how much potassium hydroxide we have in the solution. So we multiply by our molarity, 0.158 moles over liters. Liters cancel, we've got the number of moles of KOH. Now, since we're in moles of KOH, we can use our balanced chemical equation. We can use the solution stoichiometry to help us out here. The two things we care about are the potassium hydroxide and the sulfuric acid. Since we've got potassium hydroxide, the 2 KOH is going to go on the bottom, the 1 H2SO4 is going to be up on top. So this lets us know how much sulfuric acid we had, or would have reacted with the amount of KOH that we added. So now we know the moles of sulfuric acid. We can calculate concentration, since concentration molarity is moles over liters. So we're going to take the moles that we have here, divide it by our liters. 20.0 milliliters is 0.0200 liters. So you can either get an answer out and then divide by the volume, or you can just do it all in one step, like I'm doing here. So this gives us units of moles over liters, H2SO4. Questions about any of the parts of doing that? Calculation. Did I do too many things at once? Would you like to see it a different way? There is also secretly a little sneaky thing that you can do. For those of you that feel perfectly fine following along with all this, we didn't actually have to convert out of milliliters. Since we had milliliters for both of our units, the milli units would cancel. So we'd have a milli up here, we'd have a milli down here, the millis would cancel. So you don't actually have to convert it out of milliliters and back, or both of them out of milliliters. But again, it's always safer to go ahead and just do the conversion. Okay, we end up with concentration of 0.0903. And if we wanted to, we can change that moles over liters back into molarity. Does this seem like a reasonable answer? Yes, it seems like a reasonable answer. And the reason that I'm saying that is we had similar volumes of our two things. We've got a ratio of 2 KOH to 1 H2SO4. So we should have basically a 2 ratio roughly between our molarities. And that's kind of what we have. We have 0.09, 0.158. It's a little more than half the concentration. It's in the same ballpark. We didn't get like 50 times the concentration. That would be crazy. All right. The other type of reaction that we very briefly mentioned was gas evolution reactions. So these are reactions that produce gas. In a gas evolution reaction, we're again using two aqueous solutions typically to form a gaseous product that bubbles out of solution. Some of these produce gas directly. So for example, in K2S, potassium sulfide and sulfuric acid, the sulfide swaps and picks up the hydrogens and produces hydrogen sulfide gas, which I think is very stinky and also maybe a little toxic, or more than a little toxic. I don't remember off the top of my head. Not something that you would want to be smelling, although I think there's small amounts produced in one of the Chem 20 labs. So you've maybe smelled it before, actually. I think it smells like farts, because sulfur just generally doesn't smell good. There's other reactions that form gas through decomposition. So you will have to remember a couple of these intermediate decomposition products. One of them is carbonic acid, H2CO3. This is in soda. Gets produced when soda's made. That's how some of the carbon dioxide is stored. So this H2CO3, given time and the right circumstances, can go on to produce H2O. If you pull out the H2O, you'll notice that what you're left with is CO2. So CO2 gas that would bubble up out of your solution. This can also, I think, form in small amounts. If you just like leave water out at room temperature, a little bit of carbonic acid will get formed because CO2 might dissolve into it, which is just an aside, not something you'd need to know. Another example of a gas evolution reaction is the reaction of sodium bicarbonate or sodium hydrogen carbonate and hydrochloric acid. Sodium bicarbonate baking soda is often used for those like elementary school like paper mache volcanoes. You'd put a bunch of baking soda in the volcano and then you dump usually vinegar in the top, and then the acid-base reaction that goes on with that produces CO2 gas that bubbles out, and then your volcano erupts. So this is basically that same reaction. So bicarbonate can also do that. These are some intermediates that are not stable. They're unstable. So a couple of our intermediates listed here, and also one gas that can be produced, the hydrogen sulfide that we saw earlier. So we looked at the carbonate. There's also the bicarbonate. I'm not going to write that. Sulfites and bisulfites being hydrogen sulfites. So things with HSO3 in them, bicarbonates being HCO3 minus, and ammonium, like in ammonium hydroxide, will produce ammonia gas, which doesn't smell particularly nice. Kind of smells like smelling salts. Sweat can also sometimes smell like ammonia. So a couple more things to memorize because we didn't have enough already. Let's practice. You can reference the table. We want to write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So the first step is we need to write out what hydrobromic acid and potassium sulfite are. Hydrobromic acid has the hydro prefix, hydro meaning that we've got a binary acid. So we've got an acid, so we start it with H. Brom is the base for bromine, which is a 1 negative charge, so it's just HBr. This is reacting with aqueous potassium sulfite. Potassium is an alkali metal. It always forms a 1+ charge. So K+. Sulfite is the ITE ending of sulfate. Sulfate is SO4, 2-. Sulfite is SO3, still a 2-. So to get this to balance out, we would have to crisscross it. We would find out that there's actually 2 potassiums in front, so it's K2SO3. This is also aqueous. And we would take a look at, well, what happens with sulfites and bisulfites. Similar to our carbonates, which produce CO2, our sulfites produce SO2. So we're going to get some H2O that forms, some water. We're also going to get SO2 as a gas, not a liquid. And we'll also get salt, which is KBr. That's got an alkali metal on it, so it's aqueous. And then the last thing to do would be to balance it. So something that's not equal on both sides, the potassium comes to mind. So let's look at our potassiums. We've got 2 on the left, 1 on the right in our KBr potassium bromide. Add a coefficient of 2 in front of KBr to get our potassiums to balance out. When we do that, our bromides are not balanced. So we've got 2 bromides now, our bromines, and on the left side we only have 1 in our hydrobromic acid. Those are rookie numbers, got to get those up. So now we've got 2 HBRs because of our coefficient of 2, which means we've got 2 hydrogens. We've got 2 hydrogens in our H2O. The SO2 plus the O equals SO3. So we're all balanced up at this point. Questions? So again, sulfides, carbonates and bicarbonates, sulfites and bisulfites, and ammonium. Basically 4 things that you have to remember. The CO3 produces CO2 and water. The SO3 produces SO2, probably also water. Ammonium produces ammonia. I don't think it's anything too crazy. Expect at least one of these, probably one of them on the next exam. Okay, other types of reactions that we'll talk about briefly. Oxidation-reduction reactions. So oxidation-reduction reactions involve the transfer of electrons. These are electron transfer reactions. And we often shorten oxidation-reduction because that's a lot to say. It's also a lot to write. And chemists famously do not enjoy writing, at least with regards to, how many words we write. There's lots of writing in being a chemist. And so we often will just shorten these as redox reactions. So the red part from reduction, the ox part from oxidation. There's lots of redox reactions that involve the reaction of a substance with oxygen. One definition of oxidation is adding oxygen. I think this is like originally where we get oxygen oxidation from. So these are some examples. Iron can react with oxygen to form rust. octane can react with oxygen to form CO2 and H2O. Hydrogen and oxygen can react to form water. And that one's explosive. So takeaways, oxidation-reduction reactions are electron transfer. They can involve oxygen, but they don't always. Here's that hydrogen and oxygen reaction. A mixture of hydrogen and oxygen is more explosive than either of the two just by themselves. You can also do redox reactions without combustion and without any oxygen. So sodium and chlorine gas reacting together to form table salt is also an oxidation-reduction reaction because there's a transfer of electrons that occurs. But since we don't have any oxygen present, it's not immediately clear that it's an oxidation-reduction reaction. The reason that it is because we're forming an ionic compound that's made up of Na plus and Cl minus. So sodium went from neutral charge to a 1 plus charge. Chlorine went from a neutral charge to a 1 minus charge. And so there must have been a transfer of electrons that occurred. In this case, Cl took an electron from the sodium metal. In reactions, metals tend to lose electrons. Nonmetals tend to gain electrons. This is basically just what I was saying on the previous slide. We've got sodium reacting with nonmetals, either oxygen or chlorine, to produce ionic compounds. And we can see that they're redox when we look at the charge that they have after the reaction occurs. So oxygen went from neutral to a 2 negative charge, meaning it gained 2 electrons. Sodium lost 1 electron. So that's one sign. Another sign, rather, that we've got an oxidation-reduction reaction. We've got neutral things going to produce ionic compounds. In order for those free elements to turn into the ions, they have to have gained or lost electrons. And one way that we can remember which one's oxidation, which one's reduction, is atoms that lose electrons are being oxidized. That's our definition. Atoms that gain electrons are being reduced. It feels like gaining electrons shouldn't go along with being reduced, but that's just the unfortunate way that it is. So the sodium metal was oxidized because it lost an electron. Oxidation is loss of electrons. Reduction is gain of electrons. And so that's where we get this mnemonic oil rig. So the sodium went from neutral sodium to 1 plus, it lost an electron. Oxidation is losing electrons, so sodium was oxidized. The chlorine gained electrons, and so the chlorine was reduced. There's another one. Leo goes grr. What kind of animals say grr? Lions. Leo the lion goes grr. And this one might be better for some of you if you don't remember the of electrons part of oil rig, because it's got electrons built into it. Losing electrons is oxidation. Gaining electrons is reduction. both perfectly good mnemonic devices to remember oxidation and reduction. So choose one or memorize both, or use some other thing. Questions so far? All right, the transfer of electrons that we were looking at, we were producing ionic compounds, and so it's very clear that one of them is getting a positive charge, the other is getting a negative charge. That's not always the case, though, and it doesn't have to be a complete transfer of electrons for it to qualify as oxidation reduction. So if we react hydrogen and chlorine together, it forms HCl. HCl is a molecular compound. It's not an ionic compound, even though it's an acid, and so it sort of behaves like an ionic compound. But it's a molecular compound. And because of the way that hydrogen and chlorine are, they don't share or hold on to their electrons in the same way. The hydrogen is a little bit weaker at holding on to its electrons, and so chlorine kind of bullies it a little bit and pulls some of the electron density away from hydrogen. And so the chlorine side of HCl gets a partial negative charge. The hydrogen side gets a partial positive charge. And so while there's not a formal change of hands of electrons, there is a change in the electron density. Basically, how often does the hydrogen get to have the amount of electrons we'd expect it to have? How often does the chlorine get to have the amount of electrons that we would expect it to have? More often than not, in this case, chlorine is going to have more electrons than we would expect. That's where we get the partial negative charge. So we've got an increase in electron density. Reduction is gain of electrons, or gain of electron density for chlorine. And the electron density around hydrogen is decreased. So we've got a loss of electron density for our hydrogen. So the hydrogen was oxidized. One thing that can be helpful for us is having a big complicated set of rules. It's not really that big or that complicated. But oxidation states and oxidation numbers can be helpful for tracking what got oxidized, what got reduced, and by how much. So this is arguably the closest that we get to playing a game because it's just a made-up system of keeping track of electrons. So we assign a number, an oxidation state or an oxidation number, to each of the elements in a reaction. This tracks electrons before and after a chemical reaction. And we've got some rules for how we do this. Please note that the oxidation states are not ion charges. Oftentimes they will coincide with ion charges, but they're not the same as ion charges. That can be a little bit confusing. So they'll often be the same numbers. Again, this can be confusing, but they're not ion charges. They just happen to be the same. Ion charges are real and measurable. Our oxidation states are imaginary. It's kind of like counting cards, I think would be one way of thinking about it, but the context, of course, and the use is different. Okay, so our rules for assigning oxidation states. These rules also have this priority list. So we do them in order. We assign them in order because the things that come first are the most important. The things that come later are less important. So our free elements have an oxidation state of 0. So copper normally exists as Cu. Chlorine normally exists as Cl2 because this is one of our diatomic elements. So if you see an element by itself, that typically means it's got an oxidation state of 0, which coincides with its charge. Again, it's not charge. If we have monoatomic ions, so where it's just one ion and it's got a charge, one atom and it's got a charge, oxidation state equals charge. the number is the same. So calcium 2 plus has an oxidation state of +2. Cl minus has an oxidation state of -1. Not too bad so far. The sum of oxidation states of all the atoms in a neutral compound is 0. So H2O has no charge. It's a neutral. It's got an overall 0 oxidation state. So whatever the hydrogen has, whatever the oxygen has, those have to balance out that the overall is 0. And if it's an ion, then it's the same as the charge of the ion. So NO3 minus has an overall -1 oxidation number or oxidation state. So whatever the nitrogen has, whatever the oxygens have, that has to balance out to a net -1. When they are in compounds, metals have positive oxidation states equal to their ion charge. So sodium in sodium chloride, sodium is going to have a 1+ charge because it's an ionic compound, and it normally has a 1+ charge. And so it gets a +1 oxidation number. Calcium normally forms a 2+, and that's also what it has here because we've got 2 fluorides on it. So our calcium is going to have a +2 oxidation number or oxidation state. So that's for our metal cations. Do we have questions so far? Okay, we'll wait a little bit because people are writing. All right, we do have more rules. It's not just these 4 rules. In their compounds, nonmetals have oxidation states according to this table that we see here to the right. And this is also hierarchical, so things that come higher on the list get priority. So for our nonmetals, fluorine is at the top of the board. So fluorine basically always gets its preferred -1 oxidation state. After we've assigned fluorine a -1 oxidation state, we can then assign any hydrogens that are left over a +1 oxidation state. The next priority is oxygen, which gets a -2 oxidation state. And then the rest of our 7A halogens, our 6A chalcogens, our 5A pnictogens get their respective -1, -2, -3. It might be helpful to point out, to notice that these numbers are the same as the charge that they would normally form. We do have to do them in priority order from top to bottom. And there are some cases where we'll have that actually making some effect, making things like oxygen not take its preferred -2 oxidation state. You can also have fractional oxidation states. And then our sign is written before the number for oxidation states. It goes after the number for ionic charges. It's important for me that you do this so that I know that you're talking about the oxidation states and not the charges, or you're talking about the charges and not the oxidation states. It also may be helpful for you keeping track of which is which. Question?
Could you give us an example of how that
The plus coming first versus after.
Yeah.
It's like calcium 2 plus. The 2 plus here is the charge of the calcium, but it has a +2 oxidation state. So the charge comes first. It's how we normally write it for oxidation states. For ions, that's the one that's like backwards from how we would have typically written numbers prior to chemistry.
So for oxidation state, you would write Ca +2 instead of Ca2 plus.
So if we were doing this in a compound, I would typically just write it above. We'll see some examples of that. Okay, so we want to practice some of these rules, assign some oxidation states for each of the atoms. And I think we do have some, yeah, we've got some coming later where we'll have the full, like, doing an equation thing. So let's assign some oxidation states. We've got chromium. It's just chromium. It's by itself. What charge do we give an element that's by itself? 0. So chromium has a 0 oxidation state. I'm putting the line through it so that we know that it's a 0 and not an O. Now we've got chromium, but it's charged. It's an ion. What's our oxidation state for things that are charged? It's the same as whatever the charge is. So this is +3. We've got next CCl4. So we've got a compound. What's the overall oxidation state for CCl4? The whole thing together. Is it charged or is it neutral? It's neutral. Since it's neutral, its overall is going to be 0. So overall 0 oxidation state. So we have to assign oxidation state values for carbon and for chlorine, and it'll have to end up being neutral. So we've got nonmetals. We refer to our list. Fluorine's first, hydrogen second, oxygen's third. We don't have any of those. And then group 7A, which is our halogens, is next. We have a halogen. So we're going to give our halogen the -1 oxidation state. So in CCl4, chlorine gets a -1 oxidation state or oxidation number. How many chlorines do we have? 4 chlorines. Each of them has a -1. So we've got a total of -4 from our chlorines. Carbon takes whatever it needs to balance out that -4. So carbon gets +4. For SrBr2, strontium bromide, we've got an ionic compound. In an ionic compound, the ions have oxidation number equal to their charge. So Sr, strontium, normally takes a 2+ charge. So we're going to give it a value of +2 for its oxidation state or its oxidation number. Bromine normally gets a -1 or 1- charge. So we're going to give it a -1 oxidation state or oxidation number. SO3 is another neutral compound. Overall 0 oxidation number. So this means that we go to our list. Fluorine's at the top, then hydrogen, then oxygen, then 7A, 6A, 5A. We've got oxygen, and it's higher on the list than sulfur. which would show up in the 6A. Let's look at that so we can see it visually. All right, we've got oxygen. It's our third entry on our nonmetal list. Sulfur would be in this 6A, so oxygen gets priority. So we're going to assign oxygen its preferred 2-. So SO3, oxygen gets -2 for its oxidation number. We've got 3 of them. So we've got an overall -6 coming from our oxygen for the oxidation state. So sulfur takes the balance. So it's going to be +6. And then we've got a charged compound. Overall -1 oxidation number. So whatever our nitrogen has, whatever our oxygens have, we have to end up with a 1- charge. And again, we're going to our list for our nonmetals. So we've got nitrogen and oxygen. Oxygen shows up on the list before nitrogen, which would show up in group 5A. So oxygen gets its preferred -2. So NO3-, our oxygen gets the -2 that it likes. 3 times -2 equals -6. Our overall is -1. So what value do we need to add to -6 to get to -1? Yeah, we need a +5. So our +5 plus 3 times -2 equals -1. There's other ways that we could algebra our way to that. Questions about any of those?
Is the overall charge for the strontium bromide, is the overall charge 0?
Yes. SRBR2 is 0, since we've got a +2 and we've got 2 -1s. Other questions? All right, so the way that we would use oxidation states or oxidation numbers to identify redox reactions is that oxidation is an increase in oxidation state. Oxidation means our oxidation number goes up, which I feel like makes sense. And reduction means that our oxidation state goes down or is reduced, which I think also makes sense. So how we would calculate this for something like carbon reacting with sulfur, initially they are 0 oxidation states because this is how they just exist naturally, normally. Sulfur could also have, I think it's S6 or S8, one of those. But this is just sulfur by itself, monoatomic sulfur. And when they go in to form their compound, carbon disulfide, sulfur is higher on the priority list for our nonmetals. It shows up here in this group 6A. Carbon's not even on the list, so carbon just gets to take whatever else is left. So sulfur gets its preferred -2. Since we've got 2 of them, that's an overall -4, so we have to assign a +4 to carbon. So based on our oxidation numbers, carbon goes from 0 to +4. Its oxidation state or oxidation number goes up, so it's oxidized. Sulfur goes from 0 to a -2, which is a reduction in its oxidation number, so sulfur is reduced. We might also want to have our oil rig definitions or Leo the line goes Gur definitions, because sometimes we can just use that instead of oxidation states. So here's how this might play out in practice. Use the oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So we get to come up with a whole bunch of oxidation states. Some of them are easy, some of them require a little more work. And since we've got a bunch of different things, it's not entirely clear right away what went up, what went down. So we'll assign some values. Tin is the first thing that shows up. Tin's by itself, so it gets what oxidation number? 0. Tin normally exists as monoatomic SN, so it gets a value of 0. The next thing that we might want to assign a value to is our SNO4. SNO4 is ionic, so we can just assign oxidation states based on what the charges are. So we've got oxygen. Oxygen's going to get a -2 because it's going to have a 2 negative charge. It always forms a 2 negative charge. And our tin is going to have what charge? It's going to have to be +4. So tin's a +4, oxygen's a -2. So just with those two things, we've already figured out that tin had a change in its oxidation state. So tin's one of the two things that we're dealing with. And then we've got some other stuff that we get to assign. We can do H2O next. So H2O, hydrogen, and oxygen both show up on our list. Fluorine, hydrogen, oxygen, 7A, 6A, 5A. So hydrogen shows up above oxygen, so it gets its preferred +1. Conveniently, that leaves oxygen with its preferred -2. And then I'll do NO2 next, because I think that's a little easier than HNO3. So NO2 is neutral, so it's going to have an overall 0 charge. Oxygen shows up on our list. Fluorine, hydrogen, oxygen. Then 7A, 6A, 5A. 5A would be where nitrogen shows up, so nitrogen gets to just take whatever. So oxygen gets its preferred -2. -2 times 2 is -4. And so nitrogen gets a +4. Questions about any of these? All right, then our last one, HNO3. These are all things that show up on our list. We've got hydrogen, nitrogen, oxygen. Hydrogen shows up first, so we assign hydrogen its +1. Oxygen is also in the compound, so we give it its preferred -2. And then poor nitrogen, again, takes just whatever is left over. And since this whole thing, the nitric acid, is neutral, it has to balance out whatever is left. So we do our +1 for hydrogen, our -2 for our oxygen, +1 plus whatever we have for nitrogen, +3 times -2 for our oxygen has to equal out to 0. So +1 -6. This would turn into x minus 5 equals 0. So x is 5, meaning that nitrogen has a +5 oxidation state in nitric acid. So nitrogen is the other thing that changed numbers. So tin changed from 0 to +4. Nitrogen changed from +5 to +4. Which one of these was oxidized? Tin. Tin was oxidized since oxidation is an increase in oxidation number. It also, because it went into an ionic compound, it also, we could see from that, lost electrons. Because it went from tin to tin 4+. And nitrogen was reduced because the oxidation number decreased. Everything else had the same oxidation state on the left and the right. So those are the only two things that changed. Questions? All right, just to show us one instance where this list can cause things that are on the list to have different values than they have. I think the classic one is H2O2, which is hydrogen peroxide, often used for like whitening or bleaching. So for hydrogen peroxide, we've got hydrogen on the list, and it's higher up than our oxygen. So hydrogen gets its preferred +1. So we've got overall +2. To balance that out, we need an overall -2 across our two oxygens, and so oxygen takes on a -1 for its oxidation state, which is not normally what it likes. So stuff like this can happen sometimes. All right, that'll do it for lecture.